Welcome back. In this section, we'll be talking about rational functions. We're going to begin in this video with some properties of rational functions, and then towards the end of this section, we'll start doing some graphing of rational functions. First, just to begin, remember that any rational function is just a fraction, essentially, where the numerator and the denominator are polynomials. So every rational function has this form of some polynomial divided by some polynomial. That means that unlike polynomial functions from the last couple of sections, we'll have to be worried a little bit about the domain for these functions, because any value of x that might make the denominator 0 would be an excluded value, and that of course means it's excluded from our domain. As always, just like with any other kind of fraction, to be in simplest terms, it means to not have any factors in common between the top and the bottom, except for 1 and minus 1. And of course, the only way you'll know if it's in simplest terms is if your polynomials for the top and bottom are in factored form. So for any rational function that we're going to look at in this section, if it's not already in factored form, we will factor it. And then we're going to think about what the excluded values will be, and we'll think about our domain then. One thing to remember, of course, as always, and we said this in earlier sections as well, simplifying a function will not change its domain. So if we start off and decide that f of x has a certain excluded value, even if we simplify the function so that it looks like the excluded value is no longer excluded, well, too bad, it still is excluded. If a function has an excluded value at the beginning of its life, then even if we simplify it in any sort of a way, that value will still remain to be excluded. Also, one thing for future, since a lot of the things that we're going to be looking at are easiest to spot when our polynomials are in factored form for top and bottom, then once we've done our factoring and simplification, we're going to leave our rational functions in factored form. Okay, so for this first example, we just want to write this rational function in simplest terms, and so before we can do that, we need to factor both the top and the bottom. The top factors nicely as a difference of squares. And the bottom also factors not too terribly either, x minus 2, x minus 3. And the x minus 2's cancel, which means f of x in simplest terms should just be x plus 2 over x minus 3. Now, if we're looking at the f of x on this line, you can see that there are two values that are excluded. We have two excluded values. X could not be 2 because that would have made the denominator 0, and also x could not be 3 because that would have also made the denominator 0. Even though the x minus 2 got factored out, 2 still remains an excluded value. So even though this looks like it should be fine to put in a value of 2 for x, the fact remains it's still excluded, even though the x minus 2's got cancelled. Which means that for my domain, and I'm going to write this in interval notation, it's going to be all the numbers up to 2, together with all the numbers between 2 and 3, together with all of the numbers that are larger than 3. So we have our two excluded values, 2 and 3, and the next part that we'll need to think about is what's happening on our graph for that excluded value of 2 and for that excluded value of 3. And that's something that's going to be the case for any rational function we look at. If we have excluded values, that's going to tell us something about what the graph looks like, and we'll need to figure out what that something is. There are two options as to what can happen with one of those excluded values. Either we'll have a vertical asymptote, or we'll have a hole in the graph. So to begin with, when we're deciding which is which, deciding whether we have a vertical asymptote or a hole in the graph really is going to depend on what did our function look like before we simplified and what did it look like after we simplified. So if we're looking back at the previous example, we might notice that we had two different factors in the bottom that gave us excluded values. There was 2 and there was 3. One of those factors we were able to get rid of completely. We were able to get rid of the x minus 2 so that that factor that gave us the excluded value was gone, versus the x minus 3. That factor gave us the excluded value, and that factor remains there once the rational function is in simplest terms. This is how we'll decide whether it's a hole in our graph or whether it's a vertical asymptote. If we have a factor that remains once we're in simplest terms, that's telling us that we'll have x equals 3 as the location of a vertical asymptote. The x minus 2 that we had as a factor and were able to completely get rid of, because that was the case for x minus 2 as a factor, that's telling us that the location of a hole will be when x is equal to 2. Now, we have to be a little bit careful here. Two things to remember. The first part is that a hole is a point, and we're going to be plotting it. We're going to be plotting it as we did back in the section 3.2 when we did piecewise defined functions. We show holes as a hollow circle drawn on our graph, and we're going to have to label the coordinates for that point, which means that although we know on the previous example we'll have a hole when x is 2, we'll also need to know what the y value is when x is 2. And for that we'll use the simplified version of our function. If we're talking about the vertical asymptotes that we'll have for our graph, we'll have to find the location of it and then draw it on our graph. And I will usually be drawing my vertical asymptotes as a little dashed line. And just like we did when we graphed 1 over x and 1 over x squared in earlier chapters, we'll also have to label those vertical asymptotes on our graph. So if you have a vertical asymptote, for example, in the previous example of x equals 3 as the vertical line, then we'll have to plot that line and label it with x equals 3. Okay, so let's just do a couple of examples of finding the locations of holes in vertical asymptotes. So we'll begin, as always, with a little bit of simplification. Here, this is already given to us in factored form, so simplifying is not too hard to do. The x minus 2's can cancel, and I can cancel one of the x minus 3's from the top and the bottom. So in simplest terms, I just have x in my numerator and an x minus 1 and an x minus 3 in my denominator. Okay, so if we're looking back at the original function that we had, we could see there were 3 excluded values. Clearly there was a 1 excluded value, a 2 as an excluded value, and a 3 as an excluded value. The x minus 2, that gave us the excluded value of 2, that factor was completely removed. So that's telling us that x equals 2 is the location of a hole. Of course, we need to know where the y-coordinate for that hole is, and to find out the y value, we'll be putting 2 into our simplified version of f of x. So to find out what y is, we'll put 2 in for x. And I get negative 2. So the point 2, negative 2, if I were graphing f of x, I would graph it as a hollow circle. I would label it 2, negative 2. So when I would plot this, my graph will do something until it gets close to that point and then move on and do something else afterwards. So I would have something like this on my graph if I were graphing f of x. All right, so the next part is for us to think about the vertical asymptotes. And again, going back to our excluded values, 1, 2, and 3 were excluded values. And the factors that gave us those excluded values are still there for 1 and for 3. So even though we did a little bit of canceling, we canceled an x minus 3, there still is an x minus 3 in the denominator, which means x being equal to 3 is going to be the equation of a vertical asymptote. Same thing with x being equal to 1. That will also be a vertical asymptote. So we'll just say that we've got a vertical asymptote at x equals 1 is one of the lines, and x equals 3 is the other one of the lines. I do want to say one thing before we do another example, and that's just a reminder that vertical asymptotes are lines, and so we need to give them as the equation of a straight vertical line. X equals 1, x equals 3. If I were to just say that the vertical asymptote is 1 and 3, that would be wrong, because 1 and 3 are numbers, and numbers are by themselves are not lines. 1 is not a line. X equals 1, on the other hand, is a line. Similarly, 3 is not a line, however, x equals 3 is a line. So for my vertical asymptotes, x equals 1, x equals 3, and we've got our hole on the graph at 2, negative 2. All right, another example. So this one is not in factored form yet, so I will need to factor the top as well as the bottom. And so if I'm looking at this, I can see that I definitely have two excluded values, 3 and 4. And I can also see that the factor x minus 3 that gave me 3 as an excluded value, that got canceled away. So I know that I'm going to have a hole when x is equal to 3. And of course, if I want to know the y value, I need to put 3 into my simplified version of g of x. So 3, negative 6, that would be my hole that I have in my graph. And the other excluded value that I had was 4, and that came from the factor x minus 4, which is still there in my simplified version of g of x. So that means I have a vertical asymptote, x equals 4. All right, so I just want to say one last thing here before we end this video, and that's for these examples, they both had holes and vertical asymptotes, but be aware that not every rational function will have holes, not every rational function will have vertical asymptotes. It's possible that I could give you a rational function and it may not have any vertical asymptotes, and it also may not have any holes.